In this videotape, we will study ellipses and hyperbolas. The graph of an equation of the form x squared over a squared plus y squared over b squared equals 1, where a and b are positive constants is called, and a is not equal to b, is called an ellipse. In standard position. If we have an equation of this form, x squared over a squared plus y squared over b squared equals 1, a is not equal to b, a and b are positive constants, we call this an ellipse in standard position. Let me give you a specific example. Let's say we have x squared over 16 plus y squared over 25 equals 1. Okay? This is like x squared over 4 squared plus y squared over 5 squared equals 1. Notice it's in this form, x squared over a squared plus y squared over b squared equals 1. By the way, these numbers do not have to be perfect squares. Okay, now, what we're going to do here is to try to find the x and the y intercepts for this curve. If x is equal to 0, you can work from this part here or from the original equation. If x is equal to 0, this drops out. Y squared over 25 equals 1. Multiplying both sides by 25, we get y squared equals 25. Y is equal to plus and minus 5. And of course, you could see it from here, too. Y squared is equal to 5 squared y is plus or minus 5. And if y is equal to 0, trying to find the x-intercepts, this drops out. X squared over 16 equals 1. Multiplying both sides by 16, x squared equals 16. X is equal to plus minus 4. Okay, so we have 2 x-intercepts and 2 y-intercepts. Let's mark them off. We have x-intercepts at 4, 0, minus 4, 0, and the y-intercepts are 5 and minus 5, so go up 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5. And now try to draw an oval-shaped curve through these 4 intercepts, something like this. You can plot some more points to convince yourself that this is really the shape it's going to take. The ellipse basically has an oval shape, and what we're talking about here is an ellipse in standard position, one whose center is at the origin. Okay? This ellipse is symmetric with respect to the y-axis. Okay? What happens to the right of the y-axis also happens sort of reflected on the left side of the y-axis. It's also symmetric with respect to the x-axis. Okay? It's an ellipse in standard position. Let's look at another one. Let's sketch the graph of x squared over 49 plus y squared over 9 is equal to 1. Once again, this is in the form x squared over a squared plus y squared over b squared equals 1. This could be thought of as x squared over 7 squared plus y squared over 3 squared equals 1. To get the intercepts, if x is equal to 0, y squared over 9 equals 1, y squared equals 9, y equals plus or minus 3, and if y equals 0, x squared over 49 equals 1, x squared equals 49, x equals plus or minus 7. Actually, you could work directly from here. It turns out that the x-intercepts are always going to be plus or minus a, and the y-intercepts will always be plus or minus b. Remember, it's x squared over a squared plus y squared over b squared equals 1. Okay, so plus and minus a, plus and minus 7 in this case, are the x-intercepts, and plus or minus 3 are the y-intercepts. Once again, let's put down the 4 intercepts, and since we know it's an ellipse, let's sketch an oval-shaped curve through these 4 points. Okay, so we have x-intercepts at 7 and minus 7. Our y-intercepts at 3 and minus 3. And trying to draw a nice oval-shaped curve through this. Well, we try. See how we can fix it up a little. Does that help? Obviously, if you could plot a few more points, you'd have some help in sketching this. You get the idea. By the way, when A is less than B, okay, that means that the x-intercepts are closer together than the y-intercepts. We get sort of a narrow, tall ellipse. That's when A is less than B, when the number under x squared is smaller than the number under y squared. It means the distance between the x-intercepts is going to be less than the distance between the y-intercepts. We're going to have one of these sort of tall, narrow ellipses. When, however, the number under x squared is bigger than the number under y squared, that means the distance between the x-intercepts is greater than the distance between the y-intercepts. We're going to get a sort of flat, wide ellipse. This ellipse is sort of running up and down, and this one left and right. Okay, and it's determined by the x and the y-intercepts. Okay. Now, this is our equation of an ellipse in standard position. Sometimes the curve that we're sketching doesn't look quite like this, but it can be put into this form. Let's say we want to sketch the graph of the equation 9x squared plus 4y squared is equal to 36. Okay. If we were to divide both sides of this equation by 36, that is, divide all parts, every term by 36, we would get x squared over 4 plus y squared over 9 is equal to 1. And in this form, we would certainly see that it is an ellipse in standard position. That is, x squared over 2 squared plus y squared over 3 squared equals 1. And to sketch it, if y equals 0, x squared is 4, x is plus or minus 2. The x-intercepts are plus and minus 2. The y-intercepts, of course, are plus and minus 3. You can just see this because this is 2 squared and this is 3 squared, or you can actually say, I'll let x equals 0, y squared equals 9, y is plus or minus 3. And here we go. In this case, of course, A is equal to 2 and B is equal to 3. Okay, now I want to change this equation just slightly. What I'm going to do is just change this plus sign to a minus sign, and it's going to completely change the curve that we get when we sketch the graph. The curve that we get in such a case is called a hyperbola. Let me give you the equation. The graph of an equation of the form x squared over a squared minus y squared over b squared equals 1. If this plus is replaced by a minus, or there's also another hyperbola if this plus is replaced by a minus. So you'd have minus x squared over a squared plus y squared over b squared, but generally we write it the other way around. The graph of an equation of the form x squared over a squared minus y squared over b squared equals 1, or of the form y squared over b squared minus x squared over a squared equals 1, where a and b are positive constants, is called a hyperbola in standard position. Now, if either of these minuses had been a plus, we, of course, would have an ellipse. By changing basically the sign of one of these terms, either the plus x squared over a squared to a minus or the plus y squared over b squared to a minus, we have changed the curve to a hyperbola. Let's try to sketch the graph of a hyperbola in standard position. And let's look at x squared over 4 minus y squared over 9 equals 1. Okay, let's try to get the intercepts for this curve. If y equals 0, we get x squared over 4 equals 1. Multiplying both sides by 4, x squared equals 4. X is equal to plus or minus 2. 2x intercepts. If, however, we set x equal to 0 and try to solve for y, if x equals 0, we get minus y squared over 9 equals 1. X equals 0, get minus y squared over 9 equals 1. Multiplying both sides by, let's say, minus 9. Okay, well, first you can multiply both sides by 9. Minus y squared equals 9. Multiplying both sides just by 9, and then multiplying both sides by minus 1, we get y squared equals minus 9. And we cannot find any y-intercepts because we would try to take the square root, and you can't take the square root of a negative number. Okay, you would not get a real answer. We're only interested, of course, in real points, something that we could plot. Since we cannot solve for y, there is no real number whose square is minus 9, we say there are no y-intercepts in this case. Okay, we see there are 2 x-intercepts and no y-intercepts. Okay, so far, what do we have? Okay, we know that there are x-intercepts at 2 and minus 2, but that's all we have. Let's try to get some more points on this curve just by plotting points, making a table of values. Just a few to get the idea of what's going on. We're talking about x squared over 4 minus y squared over 9 equals 1. I would like to first solve the equation, say, for x or for y. Let's try to solve it for x. I'm first going to clear fractions by multiplying through both sides by the LCD, which is 36. So we have x squared over 4 minus y squared over 9 equals 1. And we're going to multiply both sides by 36. So we'll get 4 into 36, 9x squared minus 4y squared equals 36. Each term gets multiplied by 36. 4 into 36 goes 9 for 9x squared. 9 into 36 4 times for the 4y squared. Then we can say 9x squared is equal to 4y squared plus 36. X squared is 4y squared plus 36 over 9. X is equal to plus or minus the square root of 4y squared plus 36 over 9. Okay, let's see what we get. We've already substituted in, for example, y equals 0, because we know when y equals 0, we get the square root of 36 over 9, the square root of 4, plus or minus the square root of 4. That's the x equals plus or minus 2 that we already have. So let's try something else. Okay, let's just try, for the sake of argument, y is equal to 4. I'm just picking this because it so happens that we get a perfect square under the radical. Of course, you wouldn't know that, you know, just starting out, but I'm just trying to get us some more points without too much difficulty on this hyperbola. So I let y equal 4, and I see that x is equal to plus or minus the square root of 4 times 4 squared plus 36 over 9. Now, 4 squared, that's 16 times 4, that's 16 times 4, that's 64, plus 36. That gives me 100 over 9 here. Once again, it's 4 squared, 16 times 4, 64, plus 36, that's 100 over 9. That happens to be a perfect square. We have plus or minus 10 thirds. It's, of course, the square root of 100 over the square root of 9, or plus or minus 3 1/3. By the way, if y were equal to minus 4, we would get exactly the same answer because we'd be substituting in here minus 4. And, of course, once minus 4 got squared, it would also be 16 times 4, 64, plus 36, 100 over 9, the same thing. So x is equal to plus or minus the square root of 100/9 once again, or plus or minus 3 1/3. Okay, if y is equal to 4, or if y is equal to minus 4, you see because it's being squared here, we didn't get any different answer. We got the same answer, the square root of 100 over 9, plus or minus 3 1/3. Let's plot these points. We have actually 4 points here that we can put on our hyperbola. Remember, these are the y values, those are the x values. So we have 3 1/3, comma 4, minus 3 1/3, comma 4, 3 1/3, comma minus 4, and minus 3 1/3, comma minus 4. Let's plot those 4 points. 3 1/3, comma 4. 1, 2, 3 1/3, up 1, 2, 3, 4. Then we have also minus 3 1/3, comma 4. 1, 2, 3 1/3, comma 4 over here. Also 3 1/3, comma minus 4. And minus 3 1/3, comma minus 4, which is down here. And we could obtain other points in the same way. I realize this is not enough to convince you, but the basic curve looks something like this. Goes through the intercept, like so. I'd like you to look for a second the difference between the curve x squared over 4 minus y squared over 9 equals 1 and the curve that we sketched a few moments ago, which was x squared over 4 plus y squared over 9 equals 1. Come with me over here now. Back here, x squared over 4 plus y squared over 9 equals 1. This, you'll remember, was an ellipse. When we set y equal to 0, we were able to solve x squared equals 4x equals plus or minus 2. Here, because of the plus sign in between the terms, when we said x equal to 0, we were also able to solve for y. Y squared equals 9, y would be plus or minus 3. We had 4 intercepts, and we drew the oval-shaped curve, the ellipse, through those 4 points. By changing this plus to a minus sign over here, what happened was that we were able to keep the 2 x-intercepts. We had no longer any y-intercepts, therefore this curve cannot cross the y-axis. All right, so clearly it's not going to come this way. It cannot cross the y-axis. And the choice here, what we had is that it sort of goes out in all these 4 directions so that it never crosses the y-axis. It does have these 2 x-intercepts, the same 2 x-intercepts that the ellipse had. Okay, but from here on it branches out in these 4 directions. There is actually a way to get a slightly better idea of what is going on in the graph of a hyperbola. There is a technique for getting a better sketch without actually going through and plotting some more points. I mean, this turned out not to be too difficult, but you can imagine that if I'd chosen some other point and we did not get a perfect square, it would not be too easy to calculate these numbers. Okay, let me show you a trick, a way of getting a good sketch of a hyperbola. Back over here to x squared over 4 minus y squared over 9 equals 1. Okay. What I want you to do is temporarily pretend that this had been a plus sign. That, of course, would turn it into an ellipse, and that curve would have 4 intercepts. If this had been a plus sign, and it had been an ellipse, the x-intercepts, of course, would have been plus and minus 2, and the y-intercepts would have been plus or minus 3. Now, I realize, of course, that the hyperbola only has the x-intercepts. It doesn't have the y-intercepts, but this is a trick for sketching the hyperbola. I say, pretend it's a plus sign, in which case it would be an ellipse and it would have 4 intercepts. Then I want you to draw a rectangle that goes through these 4 intercepts. Okay, something like this. The intercepts are located, the intercepts are the midpoints of the sides of the rectangles. Okay? We drew a box. This is going to be a help in sketching the hyperbola. This is not the hyperbola. We know what the hyperbola looks like already. Okay, so we put down what would be the 4 intercepts had this been an ellipse. Now I want you to draw the diagonals of this rectangle. They will, of course, go through the origin, and I want you to extend them beyond the corners of the rectangle. Okay, so we have one diagonal, and I want you to extend it. Like so, and let's put the other diagonal in. Let's connect the opposite corners of the rectangle. They will pass through the origin and extend them. These lines that I've drawn are called asymptotes. They are useful guidelines in sketching the hyperbola. They are lines that the hyperbola sort of gets very close to but doesn't quite touch. Now, let's go back to the fact that we know this hyperbola had x-intercepts of 2 and minus 2. It, of course, did not have y-intercepts. Therefore, the hyperbola that we're looking for will look like this. It'll go through the x-intercept, and we'll get very close to, okay, we'll get ever closer to these lines. These are guidelines to telling you how wide to draw the hyperbola. As they're getting close, it's getting close but not quite touching. This will enable you to figure out how wide or narrow the hyperbola should be. Let's go through the procedure. We're going to be doing some more examples. What you do when you want to sketch the graph of a hyperbola, you know it's a hyperbola because of this minus sign here. You sort of block it out for the moment. You pretend it's a plus sign. If it were a plus sign, it would be an ellipse. If it were an ellipse, it would have had x-intercepts of 2 and minus 2 and y-intercepts of 3 and minus 3. In fact, if you'll notice, the actual ellipse that we had, x squared over 4 plus y squared over 9 equals 1, it would be the one that we would sketch in here through the 4 intercepts.